So let's kind of talk about a little bit of how we would tie these together with something called the Haber process. We said the Haber process was spontaneous at low temperatures, and it's our nitrogen gas plus 3 hydrogens in equilibrium with NH3. Or it's in equilibrium with 2 NH3. If you look at the figure in the textbook, we can plot the delta G and look at the equilibrium. Initially, if we have a point right here, we're going to pick an arbitrary point. At this point right here that I've noted, it's going to be nitrogen gas plus 3 hydrogen gas. This is before the reaction takes place. Remember that if a reaction goes forward, there needs to be some kind of driving force. And typically when you're looking at a spontaneous process, you're going to reach equilibrium. So we typically draw this process and show kind of like a well that looks like this. Over here on the other side, this would be pure ammonia, or pure NH3. This point right here at the bottom of a well is going to be the equilibrium. And at equilibrium, our Q is equal to K. Over here on this side, Q is going to be greater than K. And over here on the left-hand side, Q is going to be less than K. So the question is, how is a reaction going to proceed if we're at a particular point in this curve? And if you think about placing a marble in here, how are we going to proceed? If we're over here at this point right here, we're going to have an excess amount of nitrogen and hydrogen. If we have more nitrogen and hydrogen, that means that in order to reach equilibrium, we're going to have to proceed forward. So the spontaneous process in here is nitrogen plus 3 hydrogens, giving us 2 ammonias. If we're over here on this side of the diagram, the spontaneous process is going to shift back this way. So in this portion of the diagram, we're going to have our 2 NH3s producing nitrogen gas plus 3 hydrogen gas. So depending on what our reaction conditions will be, we're either going to be producing more ammonia, which from our perspective is good, or we're going to be producing more nitrogen and hydrogen, which we don't want to happen. So the question is, what do we need to keep in mind in an industrial process? We're trying to produce, or at least we can say here our goal is to produce large amounts of NH3. So the considerations that go into this are the following. We are saying that in this particular process, if we kind of think about this over here to the side, our delta G, or our delta G naught, is negative at low temperatures. So what this tells us is that if we look at our energy reaction diagram, so if we plot energy on the y-axis and reaction progress on the x-axis, this tells us that our reactants are going to be higher in energy than our products. And remember, thermodynamically, this is all this tells us. It does not tell us anything about the activation energy or how we get from reactants down to products. So since we have a favorable delta G, that tells us a lot about the relative energies of the reactants and the products, and that it would be thermodynamically favorable. But some of the considerations in this process, number one, we have to overcome the energy of activation barrier. So that's one thing we have to consider. From going from reactants to products, overall we're going to gain energy, but it might have to take a little bit of energy to do that first. The second consideration we need to think about is the rate. If it takes 3 years to produce 10 grams of ammonia, I don't think that's going to go very well, and we're not going to be able to, produce much of this in a reasonable amount of time. Another thing we need to think about is how can we shift the equilibrium to produce more NH3. And the last thing that we always need to think about, especially if we're in business, is money. And one thing that a businessman will tell you is that money is equal to time. So when we're looking at a particular reaction, we need to make sure we keep the kinetics of that reaction in mind, because if the kinetics don't work out well for us, we're not going to be able to produce much ammonia. So one of the things that is done in this particular reaction is that it's performed at high temperature. And based upon what we talked about here, kind of goes against what the thermodynamics would say. And typically this reaction is performed at about 400 to 500 degrees Celsius. And under these conditions, we would think that the standard delta G should be positive. But what we can do is we can manipulate these pressures. Because remember, the Q is equal to the partial pressure of the NH3, that quantity squared, divided by the partial pressure of N2 times the partial pressure of H2 to the third power. So we can manipulate Q, and typically this reaction occurs at very high pressures, and usually on the order of 100 to 200 atmospheres for most particular reactions. These are very highly pressurized reactions. All the problems in the book usually say, hey, we're going to change the pressure to 1.5 atmospheres or 5 atmospheres. This is going on at 100 to 200 atmospheres. Okay? So the reason we do this is for thermodynamics. The reason we keep the temperature high is from a kinetic standpoint. Because as we increase the temperature of a reaction, we're going to increase the probability that the collisions that happen between nitrogen and hydrogen will result in an ammonia molecule. One other thing that happens during this process, so basically let's just say we take this big huge vessel right here, and we're going to pump in nitrogen gas and hydrogen gas. And as we pump that in, our system is going to reach equilibrium down here. Regardless of what temperature we reacted at, we're going to get an equilibrium. If we wanted to push that equilibrium farther, we could add more nitrogen and hydrogen, but that costs us money to put in there. So what happens is, as this reaction proceeds, we're going to remove the NH3 from this vessel. So if we can isolate and remove the NH3 here, this is going to shift the equilibrium forward. And it's going to produce more NH3. So as we decrease our concentration, as we decrease the partial pressure of NH3, it will shift this reaction forward. It's going to change our value of Q. It will make Q smaller. And we're going to proceed farther and shift this equilibrium. So the reason I bring up this whole process is because it's still a process that's widely used today, that, like I said, was developed right around World War I, around 1918. Sometimes this is called the Haber-Bosch process. And back in the World War I era, everyone wanted to use this as an explosive. Right now we use this as fertilizers for our particular crops. So it's a very important process, and I like this, using this as an example, because it relates together kinetics and thermodynamics. And it shows the importance of each one in a particular chemical process. So don't completely forget about chapter 15 in your textbook. Okay? I'm going to tie some kinetics into some of the problems that we analyze. But unfortunately, and I think this is very, very unfortunate, the final exam for Chem 123 covers mainly the topics that we cover in this class. If it was up to me, right, and I was the chair of the chemistry department here at Ohio State, I would make the Chemistry 123 final cumulative through the entire course of 121, 122, and 123. Okay? Everybody laughs at me. Some people are shooting themselves in the head right now. Okay? But luckily, I was overridden and outvoted for that comment. So you can thank my colleagues, the vice chair, everybody like that, because stuff like this is important. And I know that's a rash example here, but keep in mind that when you're looking at a particular chemical problem, you need to keep everything into consideration, not just what we're talking about in chapter 19. And everything kind of builds on each other, and that's where we just get completely swamped, because we're like, holy crap, how do you expect me to remember chapter 15, man? Like, that was a month ago. But when we're solving more complex problems, and the more complex a problem is, the more you need to tie a bunch of things from here, there, and everywhere. In the lab, you guys are using instrumentation that combines multiple areas of chemistry, and it can use those areas of chemistry to solve problems and determine a concentration that you have in, for example, a soil sample. Okay? So keep these things in the back of your mind when you start discussing and trying to figure out a chemical problem. Okay? And those of you who are fortunate enough to take something called the MCAT, trust me, that thing's a lot worse than any cumulative 121, 122, 123 exam that I could ever think about putting together. So you pre-med students have something to look forward to with that. So this kind of is my little message for the Haber process.